Alright, so let us continue the discussion of microcontroller circuit design with S32K series. So we have already discussed various like parameters like what are the features and functionalities of this S32K microcontroller series. The device that we are using is 48-pin LQFP package and exact device is FS32K118, right? And this LF is actually indicating the 48-pin package. Okay, so let us continue the circuit design. So as we have seen here, this is the microcontroller symbol that has been arranged in port pin wise. So it is PTA0 to PTA13, similar to that PTB0 to PTB13, and we have PTC1 to PTC16, and similar to that we have PTD0 as well as like PTE. So basically we have uh, A port, B port, C port, D port and E port. Total 5 ports are there. Okay. And all the different functionalities has been assigned to the pin configuration. So we will see one by one how it has been assigned and what are the different reasons. Okay. Let us get into the some of the parts that we have here. So basically we have a reset circuit. So reset circuit is nothing but once we press this switch, this push button switch. So this push button switch will make this pin low, and this is how my microcontroller will get reset through this particular signal, reset B. Okay. And if it is not pressed, this will be pulled high, so it will allow the microcontroller to continue working. Okay. So reset B signal, you can see it is here. So this is the 47 pin number which can be used as a reset button. Similar to that, this can be also used as IO pin functionalities if you do not want to use for reset functionality. That is other process. Next is a very nice JTAG configuration is given for my programming purpose. So JTAG as well as SWD programming is also there. Okay, so serial wire debug is there as well as JTAG configuration is there. Okay, so in JTAG configuration you can see very nicely that we have JTAG TMS, TCK, TDO, TDI as well as reset pin, and we have the power button here, and we have ground button, that is pin number 3 and 5. 7 is nothing but a key, this is called as key, and 9 number is actually the detect pin. If you want, you can directly ground it, or giving it with 10 kilo ohm is recommended. Okay, so this was all about the like programming part. Coming back to the power supply decoupling part, so decoupling capacitor needs VDD. Okay, so we have VDD1 2 pin are there, so VDD1, VDD2. In that we have put extra 10 microfarad capacitor, so 10 microfarad plus 0.1 each of the pin will be getting it. For analog supply like VDDA supply, what we have done is this VDDA pin itself has been filtered out and changed it to VDDA pin. And similar to that, we have put 10 microfarad plus 0.1 microfarad will be sufficient. If you want, you can discard, like C9 and C11. Okay, so you don't need to mount them. Otherwise, for better functionality, you can keep both of them. I have put it a 0 ohm resistor directly. If you do not want to use this, you can directly use this as well, or keeping both of them together is also not a problem. So this was all about decoupling capacitor and programming. Moving to the next page, let us get into the power supply part. Okay. So as you know, power supply is very important for your like design. So what we have done is we have a power supply input connector which is going to give you a inputs voltage. So this can be taking from 6 volt to 18 volt. Okay, or otherwise if you want, you can utilize a adapter jack as well, which is generally like comes up 12 volt, like 2 ampere rating, or 6 volt 2 ampere rating. So these two adapters you can try to use. Even if you want, you can use a 15 volt adapter as well, but these are very popular 12 volt 2 amperes. Two more power will be needed here for DAC application like 12 volt and minus 12 volt. So I have given a connector with two pins. I mean, one is power, one is ground, and similar to that, negative power, negative ground. If you do not want to use this power, what you can do is this P12 volt can be utilized to give this as V input power. through this jumper. So you sort this jumper, so this 12 volt itself will be utilized to do that job. Okay, or if it is directly 12 volt coming, then you don't have to use this 12 volt separately. This V input will be taking 12 volt, and you can like sort this one to get this 12 volt if it is exact 12 volt supply. This 12 volt and minus 12 volt needs to be filtered out and like have some protection circuit. So for that purpose I have used here TVS diode of 12 volt, and here also 12 volt. So this is like reversed, because of it is negative voltage. Okay, and we have nicely put capacitors and inductors to filter out the signal. So this is how you have a filtered output voltage of 12 volt and minus 12 volt. Coming back to the power supply regulators, so to get 5 volt, that is nothing but my VCC. So this is the input voltage, which is V in A. V in A is coming from this after the fuse. Okay, so this fuse, after fuse we are getting this voltage, and this is a switching regulator from analog devices with 2.4 amperes rating. However, we are utilizing for 2 ampere rating. So this switching regulator is designed in such a manner that it can give you 5 volt output with 2 amperes output rating. And similar to that, there is a like a reset pin here. So it will keep on showing you that whether my output is fine or not. So if this LED is glowing, this is red LED. If it is glowing, it means this VCC is fine. If it goes, like reset pin goes low because this particular like regulator is not working properly. In that case, this will go low, and in that case, this will not be glowing. Okay, so this is how you will see that there is a malfunction in this particular voltage regulator. For 3.3 volt supply to my microcontroller, what I have done is this particular VCC has been used as a input here. So here I have put one like uh, jumper here. So if you want, you can sort these two. Otherwise, you can mount this resistor to get your 5 volt to VCC. Okay, so this 5 volt will be giving you a output voltage of 3.3 volt with 0.5 amperes rating, and this will be used for my processor supply. Okay, so microcontroller supply will be getting this particular 3.3 volt. So this was all about power supply. Okay, let us proceed next page. So we have some discrete functionalities. So what we have is we have one audio buzzer for beep sound. Okay, beep sound, so like t t t it will do. So this is actually run by a like buzzer signal, which is nothing but my PWM signal. Okay, so PWM of 2.71 kilohertz will be driving this particular audio buzzer. This is taken from CUI devices. Okay, so CUI devices, which is CST-931AP. Okay, similar to that, we have one potentiometer also like in the circuit. So 10 kilo ohm potentiometer is there, which is going to go directly to the ADC of my microcontroller. And this is how you vary this particular like a knob, and the resistance variation will give you a different voltage level, and this is how you will be able to evaluate your ADC with this particular potentiometer. Moving to the next stage, what we have is we have put extra 4 kilobits of EEPROM with I2C interface. So this I2C interface is pulled up here, and this is going to give you like 4 kilobits of memory. Okay, so this is taken from microchip technology. Coming back to two voltage levels, which is my 5 volt level as well as 3.3 volt level. So both of them are monitored through microcontroller with this voltage division, 30 kilo ohm and 10 kilo ohm, and this is how you are going to send it to my ADC VCC. Okay, after buffering as well as filtering. So after buffering and filtering, we are sending it to my ADC. Similar to that, same functionality is done for 3.3 volt as well, and here it is going to send to ADC VDD. Okay, so either you can utilize directly to the microcontroller ADC, or we have used one separate SPI ADC. That one will be using these two ADC functionality. Moving to the next one, what we have done is we have like two push buttons for user interfaces. So these two push buttons have been properly like mitigated with debouncing as well. So if there is debouncing, that has been avoided by using these two capacitors. Okay, similar to that we have kind of pipe filter. So this is how it is going to give you a filtered signal when you press this particular switch, and once you press this will give you a low at this user push button switch. Okay, otherwise it will be like seen as high, and microcontroller will see that it is not pressed. Once it is pressed, this will be low. Similar to that user pb1 as well. To have some permanent like configuration like high or low, we have put deep switches as well. So if you keep the slide left side, then it will be putting as low, and you keep the slide as right side, it will be getting it as high. Okay, so this is how you will be setting these two pins of the microcontroller as high or low, and based on this you can configure your like different applications or give some commands based on the understanding of this. Okay, three LEDs we have put like user LED 5, 6 and 7, and these LEDs can be like programmed based on your requirement. The thing is, we have not used IO pins so that our current consumption can be minimized. We have utilized MOSFET to drive these LEDs directly. Okay, we have given one more like a USB micro USB, so it is B type. So this one is going to power up your device using this V bus, and that can be used directly. So what we have done is, coming back to the power supply section, if you do not want to use any external power supply, what you can do is you can sort these two 5 volt and V bus. So 5 volt will be coming directly, and you don't need to use this regulator. Okay, anyway, that will be used on the mounted PCB, but this is fine. So this V bus will be giving you 5 volt, and this 5 volt will be actually converted to 3.3. So you can power this board through your laptop as well for simple like a debugging or something. But other functionality may not be able to utilize, like 12 volt and minus 12 volt application, you cannot use them. Okay, coming back to like ADC. So this is my ADC SPI interface. ADC is there. So we have a very nice inbuilt V reference ADC. Okay, so this is ADC going to be having 16-bit ADC controller with SPI interface. Okay, so what is happening is, chip select is coming from the microcontroller as SPI1 PCS0, and similar to that SPI1 SDI, that is input signal, going to go to your microcontroller. The ADC data will be going to the microcontroller, and this is my clock line from the microcontroller that is coming as a clock driver. Okay, what is happening is, we have used like 8:1 mux. So total 8 number of ADC inputs can be selected one by one serially, and this V in ADC will be coming as this point, and this will be getting buffered, then filtered, and again buffered, and then it is going to go to ADC conversion IC, and this ADC conversion data will be sent to your SPI data. Okay, the channel selection is being done by 3 IO pin of MUX A0, A1, A2, and this is being driven by the microcontroller signal. So you can keep this as 0, 0, 0. It means first one will be selected. If you keep it 0, 0, 1, second one will be selected, 0, 0, 0, 1, 0, then third one will be selected. Like that, it will be keep on happening. Moving to the next section, what we have is we have NTC. So this negative temperature coefficient is there. So let me just increase the size. It will be nice for you. So let us say like you can connect this NTC at this particular connector, and this will be giving you a variable resistance based on the temperature that is changing. So at 25 degrees centigrade, this will be 10 kilo ohm. So for 10 kilo ohm, what will happen is, this point VDD will be VDD by 2. So this particular point will be coming as VDD by 2, and I have given a provision of like a buffering, and this is going to go to your temperature NTC. All right, so this is kind of like ADC. So based on the temperature variation, the resistance will change, and this resistance change will change the value at this particular voltage node, and this node voltage will be like a differing, and similar to that we will be getting different ADC values. If you want, you can increase the gain as well if you have some other thing. So for that purpose, what you can do is you can power this particular microcontroller, particular op amp with 5 volt signal. Right now it is powered with 3.3 volts. So I understand my voltage level will never increase more than 3.3. That's the reason it is powered with 3.3 volt. Okay. Coming back to one of the photodiode has been used for ambient light sensor. So this light sensor, once it is received, it is going to get filtered, and this is going to go to your ambient sensor ADC. So this is how the ambient light sensor can be also measured, like how much ambient light is there in your environment. Okay. Similar to that, we have used a very nice, humidity sensor as well as temperature sensor both together. So we have VT as temperature sensor and RH as humidity sensor. So this IC is used from Renesas. So this Renesas IC is actually going to give you the humidity as well as temperature, and so that you can directly measure them through your ADC. So what is happening is this VT, that is your temperature, is going to go into this particular buffer, and after this, after filtering, we have ADC, temperature ADC. So temperature sense going to go to your ADC, and this is how you are going to measure the temperature of your environment. Similar to that, for measuring the humidity range, you will be having humidity sensor. And this is a complete video also that I have measured, put already for just a temperature sensor and humidity sensor. A complete video is also made already. And same circuit I have used in this particular application. Moving to the next part, yes. So we have, RS232 as well as RS485. So let us do that. So we have UART signal coming here, and this is going to get converted into RS232 signal, and this is a DB9 connector. So this DB9 connector will be giving you an output of RS232 signal. Okay. Same DB9 connector has been used for your RS485 transceiver as well. So this RS485 transceiver will be taking UART signal data, and then this is how you are going to get RS485 signal. Okay. Now what is happening is either of these two signal can be used at a time. Both of them will not be used together. So what has happened is this UART signal I have done through a analog switch, and this analog switch will be selecting either SA1, S1A and S2A. So S1A and S2A will be selecting the RS232 signal, which is going to go to these two. Okay. Similar to that, it will be selecting S1B and S2B, and in that case it will be selecting RS485 TX and RX. So this is how this guy will be selected. Okay. Now I have put it here, like what will happen, like if my low is there, so low means it will be S1B, S2B. So it means S1B, S2B. So by default it is pulled low. It means this select line is going to make sure that what will be the functionality, whether RS232 or RS485. So by default it will be working as RS485. Okay. So this RS485 transceiver will be working. Now this transceiver is actually in half duplex mode. So if you want, you can make it work as a driver as well as receiver. So to make it as a receiver, what you have to do is you have to pull this drive enable signal as low. So once it is pulled low, it will be working as a receiver. So RO output will be getting, like receiver output you will be getting. Similar to that, it is pulled high by default. So if you want, you can pull it high, and this is how it will be working as driver or transmitter. Okay. So this is how this particular IC has been used, that is ADM3061. Let us move to the next part. So what we have is we have a CAN transceiver and LIN transceiver. So let us start with CAN transceiver. So CAN transceiver, what is happening is my microcontroller signal is getting CAN 0TX and CAN 0TX and CAN 0RX, and these two signal is getting transferred through a voltage shifter or voltage level translator. So in that case what is happening is this is going to give you a high level of signal, that is 5 volt level. So this VDD is 3.3 volt and VCC is 5 volt. So my microcontroller is giving you 3.3 volt signal, and this is getting converted to 5 volt levels. Okay. And this TXD RXD signal is coming to the microchip CAN transceiver. So this is used from microchip devices or microchip technology. And this CAN 0 TXD and CAN 0 RXD is being used, and this is how it is being transferred to as CAN high, CAN low to this particular connector. So this is a header that has been used to transfer the CAN signal as high and low. That is a differential level signal. This is also used a very nice feature of split functionality. So split functionality can be utilized. Otherwise, this will be optional. Okay. Coming back to the LIN transceiver. So LIN transceiver, what we have done is we have a LIN transceiver, and this LIN transceiver will be receiving UART signal. So UART signal will be 3.3 volt levels. Okay. And we have a, like regulator output. So whatever the voltage, the supply that is there, based on that, this voltage regulator output will be there. So in that case, this voltage regulator output can be pulling this fault pin or TXC pin as high. And this lin RX lin TX, which is coming from UART, that is going to give you a lin bus output, which is lin bus, and this lin bus is going to go into the lin bus connector. So this is how you will be getting the output from this particular header. This trigger mux pin that was actually used in the like one of the pin from microcontroller, that can be used for your like triggering some application or some functionality. The power supply for this particular LIN transceiver has been used as like V in A only, or it is nothing but your 12 volt. Okay. So this 12 volt is going to get like reverse polarity protection. Then we have like protection circuit, and we have like capacitors. Even LIN bus has been protected with one TVS diode. Okay. So this is the complete process of this LIN transceiver. Moving to the next circuit, which is the very important circuit, which is going to be the ADC. Okay. So this ADC circuit, what is happening is, this is the AD5544, which is having 4 channel ADC, or sorry, 4 channel DAC. It is a DAC, not ADC. So 4 channel 16-bit DAC. And this is utilizing like voltage reference of 10 volt. Okay. So this power supply is 5 volt for this, and this is going to be having a SPI like a interface. So we have SPI 0 with PCS1, that is your like PCS1 chip select that has been used. So SPI 0 itself has been used for the purpose. And then we have SDI signal, SCK signal, and SDO signal. So all the signals are there. We have some other signal as well, like MSB signal. If you want, you can keep it always pull high, but during reset or something, you have to pull it high. Okay. Other parts is like LDAC is there, and we have like RS pin. So that is also connected to your microcontroller. Coming back to other parts, like like we have DZGND and SGFND and all these things. So for simplicity, we have right now like grounded it completely to a single ground. If you want, you can make it separate as well. So basically, we'll tell you about analog grounds. So analog grounds, if you want, you can keep it separately connected to the grounds of like your op amps, corresponding op amps. So what is happening is, the first one will take, let us say, reference feedback of A. So analog output A, that is I out A, is going to go into this particular op amp, and this is going to get filtered out and buffered, and this is going to give you the output as DAC out 1. Similar to that, you can have the functionality of DAC out 2 and DAC out 3 and DAC out 4. And all these output of DAC is going to get connected to one of the one of the output connector, and this 4-pin output connector can be used to get this DAC output. Okay, so this will be giving you a voltage output. However, the device which is going to give you is a current output. So this current output is being converted into voltage output through this particular op amps. And the best part is, if you want, you can utilize these op amps a single op amp instead of using like OPA 2197. This is a 2 circuit device. Okay. it is always recommended to use one circuit device. So you can use OPA 197. So single op amps will be used here also, here also, here also. So in that case, you will be having a very nice independent output of DAC output 1, 2, 3, 4. And this is the IC that has been used to generate the output voltage, which is going to be 10 volt reference volt. So this is ADR01. So ADR01, this IC has been used as a reference voltage IC. So all right, hope you have now a very like good understanding of complete circuit that we have done here. And let me just show it to you quickly. So this was the block diagram, and this is the microcontroller part. Then we have power supply management and everything. Then we have discrete part like buzzer and all those things. We have filters and ADCs. Then we have user IOs and USB connection. Then we have ADC and multiplexers and everything. Then we have sensors like temperature sensors, ambient sensors and all those things. And then we have RS-232 and RS-485, and utilizing one of them, this particular analog switch can control one of them. So which one you want to utilize, you can use them. And one DB9 connector has been used to get the output of RS-485 or RS-232 signal. Then we have CAN transceiver and LIN transceiver. Okay, so CAN and LIN physical layer is also there in this. Then we have used 4-channel DAC output. So this DAC output will be giving you 4 DAC outputs for your different applications that you want to use. All right, so hope you have enjoyed this, and if you do have any questions or any understanding regarding this particular circuit design or how do you want to utilize them, you can always reach out to us and we shall be able to give you a correct answers or correct design techniques that you need to have. Thank you so much.